Today we're going to talk about wave speed and how it differs from frequency. Speed is still the same thing as it's always been. It's a physical distance traveled through space in a certain amount of time. So if I take a wave and I take one point on that wave and I measure how far that point moves in 1 second, that's going to give me the speed, that distance over the time that happened. Frequency is different. Frequency is how often the wave occurs. The speed of a wave depends on the medium through which it moves. And the medium from last week is the material or the substance that the wave is traveling through. So most of the time that's air, could be water, it could be glass, but the medium is going to dictate the speed of the wave. Now, if I venture over here really quick, frequency and wavelength and speed are very closely related, as we'll see in a moment with this formula, but there's a very, very clear distinction between frequency and speed. And just because a wave has an incredibly high frequency doesn't necessarily mean that it has a high speed, meaning how fast it's traveling forward through space. It may be traveling up and down very quickly, but it might not be traveling through space very quickly. And let me show you an example here. What we're seeing here are two different waves with the same velocity. They travel forward through space at the same rate. However, the wave on the top has twice the frequency of the wave on the bottom. So frequency and speed don't necessarily correlate. You could have two waves with the exact same speed, but completely different frequencies. A couple of other examples that I like to give is, imagine you're bouncing on a pogo stick. Hopefully you know what a pogo stick is. If not, go ahead and look it up. But imagine you're jumping up and down on a pogo stick. And you may be jumping really high, you may be jumping not very high, you may be going really fast up and down. But if you're not moving forward very quickly, then your speed is still very slow. So there's a difference. Frequency would be how quickly you are jumping up and down on the pogo stick. Your speed, though, is how forward you're moving, how fast you're moving forward. Another example I like to give, and I usually do this as a demonstration in class, but I'll have two students stand up and I'll have one student just walk at a normal pace. And I will have the other student do high knees next to them. And they will move forward through the classroom at the same forward speed. But the person doing high knees has a much higher rate of steps taken per second. So the frequency of the person doing high knees is much higher than the person who is just walking, but the two of them are moving through the classroom at the same velocity. And there's a nice simple formula that ties frequency, speed, and wavelength all together. Here we go. V equals lambda F. V for velocity in meters per second. Lambda is the wavelength. This is a Greek letter. Let me go back. And so this is pronounced lambda. It's a Greek letter and it stands for this wavelength of a wave. If we look at this formula more closely, it's easy to think that if the frequency increased, wouldn't that mean that the velocity increased? Don't they seem to be directly proportional? And yeah, you're not wrong. However, if the frequency of a wave changes, that means the wavelength is going to change. These are inversely proportional. So if the frequency goes up, the wavelength is the thing that will compensate for it. The wavelength will go down. Let me draw this for you. If I have a wave with like this, let's say. Okay, here's my wave. So I'm going to pick 2 points on this wave and that are identical, let's say from here and to this matching point here. And here's my wavelength. Here's my lambda. Okay. Now, if I take that same wave and I change its frequency and I decrease the frequency, let's say, what's going to happen? Now, wavelength is much larger, but the speed of the wave was not affected. The rate at which it occurs, the cycles per second, that frequency has changed, but the wavelength also changed and the speed remained the same. So these two work together. And if we multiply them together, we can collectively get the speed of the wave. All right, Noah is standing 170 meters away from a steep canyon wall. That's a beautiful drawing. All right, here's the canyon wall. And Noah is 170 meters away from it. Okay. He shouts and hears the echo of his voice 1 second later. So the time is 1 second. What is the speed of the wave? And that's it. Now, we did just get this formula, and we're going to use it, but we don't actually need to use it yet. Because what don't we know? Wavelength and frequency. So this formula is kind of useless for us. However, we have another definition of speed that we've been using all year long, and that's distance over time. We know how much time this takes, and we can figure out how far this wave travels in 1 second. But we have to be clever real quick, or just at least be aware of what's going on. So if Noah shouts and hears the echo, that means the sound wave has gone all the way to the canyon wall, bounced off, and then come all the way back to his ear in order for him to have heard it, which means the distance is not 170, it's 340. It's twice that. So all we need to do is distance, which is 340, over time, which is 1. So the speed of this sound wave is 340 meters per second. And that is a pretty standard acceptable speed of sound in air. I'd like you to finish the rest of the practice problems on this worksheet. Try your best. The formulas that you will want in your back pocket are this newest formula, this other formula for speed that we've been using throughout the year, and our relationship between frequency and period. And we can solve it the other way. Okay, these collectively should help you complete this worksheet. If you have questions, I am here. Do your best, upload your work when you're done, and we will go over the answers at a later time. Good luck.